if you've watched the previous lessons in this unit of study, then you're familiar with ratios of stress to strain and different elastic moduli. So for example, bulk modulus is a stress to strain ratio. Now bulk modulus appears in some calculations for the speed of sound in a fluid. So this picture at the top of the page shows a jet that's traveling faster than the speed of sound, and in doing so, just in its wake, there's a region of highly compressed air, and that causes the water vapor to coalesce out of the gaseous state and back to a liquid state. So they refer to that as the vapor cone once a plane goes past Mach 1. There's a picture of a baseball stadium, and if you're sitting in some cheap seats, then you've maybe noticed that you can see the bat hit the ball well before you actually hear the sound of it, and that's because light travels a lot faster than sound. The speed of sound at standard temperature and pressure in air is about 343 meters per second. Now it travels about 4.5 times that speed in water. And we can calculate that really easily. It turns out that the speed of sound in any fluid, whether it's air, water, or any other fluid you can think of, is just equal to the square root of the bulk modulus divided by the density. And I guess we should check that dimensionally. Let me remind you what bulk modulus is all about. So if you have a material with an initial volume, say of this size, and then it has an additional pressure applied to it, pushing in from all directions, that increase in pressure beyond atmospheric pressure is the stress that's added to the material, and the resulting strain is the change in volume. So Bulk's modulus is the ratio of stress over strain. So it's the stress in the form of additional pressure divided by strain, which is a fractional change, which is the percentage or fractional change in the volume. So the units for bulk modulus, well, the denominator doesn't contribute any units because it's just cubic meters over cubic meters. So the units for bulk modulus are the same as the units for pressure, which is a Pascal, which is a Newton per square meter. So let's see what happens when we take the square root of newtons per square meter and divide it by units for density, which is kilograms per cubic meter. So this becomes the square root of, let's replace newtons with kilogram meter per second squared. And let's take the cubic meters in the denominator of the denominator and move it to the numerator. Let's take the square meters in the denominator of the numerator and put them in the denominator. And there's still kilograms here. So let's see, we have kilograms cancel out, and then meters and meters cubed give us meters to the fourth, and then those cancel with the meters squared in the denominator to give us meters squared. So it looks like we're left with the square root of meters squared per second squared, which, gosh darn it, would be meters per second, which is just what we're trying to find. So as an example, let's see if we can verify that the speed of sound in water is about 4.5 times as great as the speed of sound in air, in particular in seawater. So here we're given a bulk modulus for seawater as 2.34 gigapascal, and the density is a little over 1,000 kilograms per cubic meter. So grab your calculators. Let's see what we get for the speed of sound in seawater. Should be the square root of 2.34 giga. That's 10 to the 9th, right? So 2.34 times 10 to the 9th Pascal divided by 1,025 kilogram per cubic meter. Now we just showed how those units are going to combine to give us meters per second. So we're just interested in the numerical value in this case. And 2.34 times 10 to the 9th divided by 1,025. We take the square root of that. We get about 1,511 meters per second. We can speak a little more about the speed of sound in air. So the speed of sound in air should also be the square root of the bulk modulus of air divided by the density of air. But the bulk modulus for air, if you've studied much thermodynamics, maybe you've encountered this in a chemistry class. The bulk modulus for air is the ratio of specific heats multiplied by pressure divided by density. Now, you've definitely encountered the ideal gas law. Pressure times volume equals number of moles times the ideal gas constant times temperature. PV equals nRT. So let's make a substitution and say the speed of sound in air should be equal to the square root of gamma times, let's see, I guess this means P is nRT over V. Okay, so replace pressure with nRT over V, and all this divided by density. Now that should be the same thing as the square root of gamma times nRT over volume, and then density can be replaced with mass per unit volume. So now volume cancels out, and we find that the speed of sound in air should be equal to the square root of gamma times the number of moles divided by the mass multiplied by RT. Well, this is just the reciprocal of the molar mass, right? This would be 1 divided by the molar mass. So we have speed of sound in air actually this is the speed of sound in any gas, to be honest. And then we'll just plug in the values that we know for air in our final calculation. So the speed of sound in any gas is equal to the square root of gamma RT divided by molar mass. Okay, well the molar mass of air is equal to about 29 grams per mole. That would be 29 times 10 to the negative third kilograms per mole. The ideal gas constant, you're probably familiar with that. That's 8.31 joules per mole Kelvin. And then we're left with gamma. Now gamma is a ratio of the specific heat at constant pressure divided by specific heat at constant volume. For a diatomic gas, and that's mostly the air we breathe, right? Mainly N2, hopefully a fair amount of O2 and so on. So there's other polyatomic gases. There's a little bit of water vapor, which is polyatomic, not just diatomic. But roughly speaking, air is approximated as a diatomic gas. And for diatomic gas, the specific heat at constant pressure is 7/2 times the ideal gas constant. And specific heat at constant volume is 5/2 multiplied by the ideal gas constant. Now the ideal gas constant, the halves cancel out. So gamma is equal to 7/5, which would be 1.4. So if you grab a calculator and you plug in this case, we get that the speed of sound in air is equal to the square root of 401. And notice we haven't plugged anything in for T yet, right? We're only going to substitute for gamma, R, and M. And when we substitute these given values for gamma, R, and molar mass, then we get 401 times the temperature. So if we wanted to, we could tweak that a little bit and say the speed of sound in air is equal to, and we can multiply times 273 over 273. So 401 multiplied by 273 will give us 109,520, and then we're left with T over 273. So then we could take and separate out and say it's the square root of 109,520 times the square root of T over 273. And if you use your calculator to find the square root of 109,520, this would be equivalent to saying the speed of sound in air is 331 meters per second times the square root of T over 273. The reason we like to write it in this form is because there's something special about a temperature of 273 Kelvin that matches up with the freezing point of water. And so we could say when the temperature of air is 0 degrees Celsius, or in other words, 273 Kelvin, then we're just taking the square root of 1, and so the speed would be 331 meters per second. Now, I thought I said earlier that the speed of sound is 343 meters per second, right? Now, why is that? Well, grab your calculator and see what you get for room temperature. So take about 20 degrees Celsius, which would correspond to 293 Kelvin. And if you use this formula, I think you'll find the speed of sound in room temperature air is about 343 meters per second. Okay, so if you're interested in the speed of sound in other materials, for example, you've maybe seen an old Western or some movie where someone's got to cross a bridge and they'll put their ear to the tracks to listen for the train. If there's a train somewhere off in the distance, the sound waves are attenuated in space much more than they are through the rails of the tracks. So when you listen by putting your ear to the tracks, the vibrations will carry a much greater distance in one dimension than the way they dissipate when traveling through the air in 3 dimensions. The speed of those sound waves through the steel track can be found, not surprisingly, using this formula. Instead of using bulk modulus, we'd probably use Young's modulus for a steel train track. So the speed of sound, exactly, it turns out to be equal to the square root of Young's modulus divided by the density. So I would encourage you to do a Google search and see if you can find what's Young's modulus for steel, what's the density for steel. Now there's different alloys of steel, so pick any one of them and see if you can determine what the speed of sound would be in a steel train track.